Any sane engineer would want the losses to be many, many times larger than the gains.
Agreed. Hi, I'm Tyler Fultz. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Today we're going to be looking at another one of Kyle Hill's videos on Oppenheimer's terrible possibility, or the atmospheric ignition during the testing of the atomic bomb. Let's take a look.
In the cold, dark hours before the United States detonated the first nuclear bomb on July 16, 1945, Manhattan Project physicist Edward Teller was making everybody nervous. It was before 4 a.m. in the New Mexico desert. The sun wasn't out yet, but he was applying sunscreen. Teller was worried about a different kind of radiation.
I know Teller would later go on to design the thermonuclear bomb, which is even more powerful. That's the fission-fusion hybrid weapon that basically uses the fission to cause fusion and make an even bigger nuclear bomb. This is after the stuff with Oppenheimer, though.
Trying to relieve the unbearable tension that years of highly secretive work had led up to, fellow physicist Enrico Fermi decided to take bets. He reportedly said, quote, "Now let's make a bet. Let's make a bet whether or not the bomb will ignite the atmosphere, and if so, whether it will merely destroy New Mexico or destroy the world." A few scientists took the bet. He may have been joking at the time, but only because a number of the world's top scientists convinced themselves that the first atomic explosion would not accidentally destroy the entire planet.
So was he saying that it would just ignite the atmosphere above New Mexico and then stop? I'm not sure he follows, because he knows the original bomb wasn't powerful enough to destroy New Mexico, right? This is Fermi we're talking about.
Los Alamos Laboratory Director J. Robert Oppenheimer bet $10 against another physicist's entire month's pay that the bomb wouldn't work at all, and waited silently in a hardened bunker for the milliseconds-long transition to the nuclear age that his gadget would soon usher in. This is the true story of the day we almost set the world on fire. For most of human history, science has been comparatively tame. Galileo dropping two spheres of different masses to interrogate gravity, Newton angling a prism to
gravity. I like
the rainbow. But as the centuries passed, technology allowed humans to press onwards into increasingly extreme energy regimes. Today, experiments with kilometers-wide particle accelerators force us to at least entertain the possibility that, for example, smashing atoms together at just 3 meters below light speed could produce microscopic black holes. In 1942, we had to ask a similar existentially imperative question.
So this reminds me of, he's referencing about 10-ish years ago, the Large Hadron Collider. There was this concern that, kind of similar to this atmospheric ignition thing with Oppenheimer and his team, that it would destroy the world either by creating an artificial black hole that would just engulf the Earth, or by creating a strangelet, a pocket of strange matter that would infect and turn the entire world into a big clump of strange matter, which can't support life. I'll put a couple of links below on that. Kurzgesagt actually did a really good video on that one. But yeah, scientists do need to entertain these sort of things, just because when the risk is extreme, you need to at least address it, even if it's just a simple bounding calculation that just says, hey, this ain't gonna happen.
Would detonating the first nuclear weapon ignite the atmosphere and end all life on Earth? A few years before the first nuclear detonation, codenamed Trinity, obliterated a bleak stretch of New Mexico desert, one of the physicists on the project, Edward Teller, reportedly walked into an office with a few other scientists and asked bluntly, what would happen to the air if an atomic bomb were exploded in the air? This basic question apparently hadn't been fully considered, and so it was taken to his superiors on the project, one of them being J. Robert Oppenheimer.
Is he referring to an airburst detonation specifically, rather than a surface detonation like the actual test?
What they were worried about was the possibility of a nuclear explosion being so intense that the fission event would cause a fusion event, where atoms in the air fuse together, releasing many times more energy than if they were split.
That takes a lot of energy to actually pull off. I talk about this in another video where they go more deeper into Oppenheimer's math. But for fusion, you basically need three things. Extremely high temperature, and by that I mean far higher than that of the atomic bomb, especially since we're talking air rather than just hydrogen as displayed on this little infographic right here. A lot of pressure, so you have to pack all of these atoms together at extremely close range, and confinement time. It's got to stay in that state for a long time. Nuclear reactions are extremely fast. If you've watched any of my previous videos before, I say they happen on the order of shakes, which a shake is 10 nanoseconds. So you're multiplying by a very small number there when you look at your fusion criteria or the Lawson criterion. I'll put another link into that down below, but yeah, they weren't anywhere close. But then again, this is all fairly new territory. It'd be like trying to ask Ben Franklin about some modern electrical stuff when he was still just doing experiments with a kite. So, yeah.
This would start a runaway chain reaction that would spread promptly through all of Earth's air, emitting enough energy to vaporize everything.
Take a lot of energy to do that.
Some of the scientists were immediately skeptical of atmospheric ignition, but no one had ever unleashed the atom like this before. There's nitrogen in the air, Teller told Oppenheimer, and you can have a nuclear reaction in which two nitrogen nuclei collide, and in this process you set free a lot of energy.
That's true. You can. On stars that are even bigger than the sun's not even capable of fusing nitrogen, at least not in its current state as a main sequence star. You just need, like, the sun doesn't have enough gravity to get that kind of pressure or enough temperature. Other stars have that, though. So it does exist in nature, but ain't gonna happen on Earth.
Couldn't ignition happen? That's a terrible possibility, Oppenheimer responded. And someone had to take Oppenheimer's terrible possibility seriously. Edward Teller, Arthur Compton, Oppenheimer, and other Manhattan Project
I love it when Kyle does this. He releases these primary sources. That's one of my favorite things about watching his videos.
Physicists now needed some calculations to address two possibilities. When the gadget, as they called it, goes off, its apocalyptic energy is going to expand outwards in a sphere. If that energy causes additional fusion to happen in air, this sphere will pick up energy as it moves outwards, eventually consuming everything. That was one possibility. The other possibility was that even if the bomb caused fusion of air molecules, as the blast expanded, it could lose energy to the environment faster than it gained energy from fusion.
Yeah.
To solve this dilemma, some of the smartest men alive were tasked with calculating whether or not Earth had an ignition point. And so, the analysis began. The worst-case scenario for energy gains, the scientists figured, would come from a single reaction involving nitrogen. A fusion reaction between two nitrogen atoms will produce fusion products like magnesium, an alpha particle, and 17 mega-electron volts of energy in the form of photons. 17 MeV sounds like a lot, but it's only around a trillionth of a joule, a million times less energetic than a single snowflake striking the ground.
This is per atom, though, so that is actually a huge amount of energy. To compare it, per molecule of coal or natural gas, you're talking on the order of just regular electron volts, maybe tens, maybe hundreds of those per molecule. This is per atom of, in this case, nitrogen. Another unit is this. Millions of electron volts are also used in fission. So fissioning a uranium-235 in a nuclear power plant is the total energy of everything is about 200 mega electron volts. That includes the fission products, neutrons, neutrinos, everything that came from this. So this one you're having about 17 mega electron volts left over. That's a good bit. But in order to get those nitrogen to fuse anyway, it takes an even more amount of energy. I don't even know it off the top of my head. That's more of a astrophysics sort of thing that, again, you'd only see in really, really massive stars to give you conditions to fuse something like nitrogen.
However, the danger wasn't in a single reaction. It was in all the possible reactions. Nitrogen makes up 78% of Earth's atmosphere. If you were to cup your hands right now, there are likely 1 million quadrillion nitrogen atoms in the air that you've captured. If all those atoms underwent fusion because of a nuclear blast, just the energy in your hands would be in the gigajoule range, as though you were Zeus himself, grasping a lightning bolt.
So how much is a gigajoule? If you do the math, I think that figures out to about 1/5 of a ton of TNT. So having that just in your little hands like this that adds up real quick when you're thinking about nitrogen over, however big an area this nuclear blast is going to be, which is a atomic bomb. We're talking just the fireball by itself is on the order of a radius of between 0.5 and 1 kilometer, depending on where you exactly detonate the thing.
Knowing the worst case reaction, the scientists then estimated how many nitrogen atoms would be in the air around the gadget, how likely it would be for those particles to fuse with other particles near them, and how energetic this hypothetical chain reaction would actually be. They had the gains, now they needed the other side of the equation, the losses. In the first milliseconds after a nuclear bomb explodes, a spherical region of air is heated to star-like temperatures. In this ultra-hot plasma, products of fission and/or fusion are flying around with tremendous kinetic energy.
So star-like temperatures, we're talking not the entire sphere, but at least the areas at the very close to it, where the reaction occurs. We're getting onto the order of hundreds of millions of degrees where the reaction actually took place. Now, getting out to the actual sphere, it drops off rapidly to just a few thousand. So starting from like the cores of stars, or even hotter than the cores of stars, to like the surfaces of stars as the sphere expands outward. And again, the star actually probably had less temperature at its core in question. I mean, the sun, we're talking, I think, tens of millions of degrees Celsius. But what the sun has that is capable of causing fusion is the gravity, which creates pressure, and it holds all of the nuclei, in the case of the sun, just hydrogen and helium, which is way easier to fuse than nitrogen. The smaller, really small stuff is a lot easier to induce fusion in. The sun mainly converts hydrogen into helium, not nitrogen into magnesium. You're going to need bigger stars than that. But yeah, that's those are the other things you need. So there can get this will get you closer to one of the three conditions you need for fusion. And again, I'm talking fusing something easier than nitrogen.
Smacking into the air at the edge of the fireball, giving it energy. However, while the nuclei of these edge atoms, protons and neutrons, can hold on to this impact energy, helping to maintain the temperature of the explosion, the electrons flying about in this plasma cannot. They let go of the energy imparted to them very quickly.
Yes.
When electrons are accelerated or decelerated in the presence of an electric field, like from a charged particle in a nuclear plasma, they can trade in some of their kinetic energy for electromagnetic radiation across the spectrum. This so-called breaking radiation was the main energy loss nuclear physicists considered when imagining the Earth basically engulfed by a star.
That's a good assumption on a microscopic scale, that, yeah, for the electrons slowing down. Again, there's other things, such as just good old school conduction and convection. Conduction, not as much so, because the atmosphere is not that much of a conductor, but there's just a lot of air that as the sphere expands outwards, you just lose energy. But I can see they're doing a bounding calculation. Then sure, let's just stick with the microscopic Bremsstrahlung lung radiation and completely neglect everything else just to be overly conservative in our estimate. I've done these sort of things before when I've done calculations just to prove a point.
Knowing the main energy gains and losses in a catastrophe they did not intend, Manhattan Project scientists working out of Los Alamos worked out what would eventually go into this paper in the April of 1946. It wasn't declassified until the late 70s. Again, the fear was that Earth's atmosphere could ignite if fusion gains during the Trinity blast exceeded the energy losses. Divide these two values then, and you get a ratio that tells you how close you are to that terrible possibility of ignition. And so Trinity's safety factor would be just how much larger the calculated losses were than the calculated gains. Any sane engineer would want the losses to be many, many times larger than the gains.
Agreed.
For this ratio to be bigger than 1.
Yes.
But when the safety factor was calculated, it was just 1.6. In the complicated calculations you can read yourself, the safety factor could get as low as 1.6. Your car's engine parts have a better factor of safety than that.
No, they're just testing one specific assumption when they did that. I'm pretty sure he's going to get into that later, but just to be fair, they're testing one specific thing. They haven't multiplied all the other things together when they're looking at it. And I think I know what he's talking about when he says 1.6. It's those two curves, the production from fusion, which again, fusion's a big if. You're going to want to take that with all the salt from the Dead Sea, and then and again, you're assuming your losses are just from Bremsstrahlung radiation. Then sure, yeah, I can see how you get to 1.6 that way.
This value was low enough that if any of these scientists were off in their calculations by just a handful of percentage points, they'd be flirting with human extinction. No sane person would take a risk like this. So why did nuclear testing proceed?
So one other way of looking at it, so that safety factor ratio 1.6, I've joked in a few of my other videos, if you've seen it, that another way of saying it is, let's just say 1 + 1 is 100, because we just want to be absolutely sure we accounted for everything, and we want to be over conservative in our estimate. So we're going to say 1 + 1 is 100, just to let you know how careful we are.
And proceed for decades.
Are we saying there's a chance that when we push that button, we destroy the world? Chances are near zero. Near zero.
Just like with the Large Hadron Collider.
Theory alone. Zero would be nice.
What this disturbing factor of safety was missing was the variable of temperature. The fusion of atmospheric nitrogen and therefore civilization and the world fire would require a Trinity blast temperature of at least 100 billion Kelvin.
Bomb's not that hot.
The highest temperatures that any bomb could even theoretically produce were 1,000 times lower than this, changing the safety factor from 1 to 1,000.
The number I had in my head earlier for when I said like 100 million degrees Celsius, I don't think the atomic bomb was that hot. Now some of the bigger bombs later, the ones that use nuclear fusion as part of their design, the thermonuclear bombs, they can get that hot, but a pure fission bomb, I don't remember the temperature off the top of my head, but it's not going to get nearly as hot as a bomb that also includes fusion as part of its design. And yes, when they use fusion, they're fusing stuff like hydrogen to helium, hence the term hydrogen bomb. They also have lithium-3 in there, or helium-3. Things that are really small, smaller than nitrogen with an atomic number of 14. So little 1s, 2s, and 3s.
From this value, the original report concludes that, quote, it is shown that whatever the temperature to which a section of the atmosphere may be heated, no self-propagating chain of nuclear reactions is likely to be started. End quote.
And that's
However,
just temperature by
though
itself.
the Manhattan Project scientists didn't identify any bomb that could feasibly lead to the end of the world, that doesn't mean they didn't calculate one. Just in case the huge safety factor wasn't enough to quell private concerns, the 3 scientists writing the original paper calculated the minimum volume of air that would have to be heated up to that 100 billion Kelvin temperature and the energy required to do so. They figured out that not only would a nuclear blast have to create a sphere of air 10,000 times hotter than the core of the sun in order to sustain a nitrogen fusion chain, that sphere of air would have to be over 100 meters wide.
That is huge. So being able to exert that sort of pressure on something that big would be insane. I don't think the entire world's nuclear arsenal, if you could somehow miniaturize it in one zone or set it off all at once, could get anywhere close to that. Because again, the 100 billion degrees isn't going to be in a very large area. It won't even hit 100 billion degrees. But yeah, that's... It's cool that they looked into it. I love it. As someone who used to like calculate how powerful like the weapons in Star Wars were, this is getting to be how powerful we're getting, like crazy Star Wars weapons or something like that.
And to do all of this, it would require an amount of energy equivalent to 20 times more energy than is contained in the current world supply of nuclear weapons.
And you'd have to concentrate it to such a small area, too. That's going to be even harder.
When the Little Boy nuclear bomb was dropped on Hiroshima, Japan, just a few weeks after the Trinity test in the August of 1945, it contained 64 kilograms of uranium-235. But when it detonated, less than 1 kilogram underwent fission. The total amount of energy released that day was from just half a gram of mass turning directly into energy. To set the whole world on fire, the Los Alamos scientists reassuringly calculated would take roughly 1 million times more material than this. A bomb with 1.5 million kilograms of uranium reacting with 100% efficiency.
And the little boy being so inefficient was mainly a geometry thing. It just sent a mass from, it was basically a little gun. It just sent a chunk of uranium towards another chunk, kind of like that. Whereas you'll see in other designs, such as the Fat Man, it was a sphere, and the sphere with the implosion mechanism kind of surrounded it and pushed it in and made it more efficient. A lot more efficient than Little Boy, but nowhere close to 100%. It was more like 10% efficient. And it also used plutonium in there, so you didn't need as much material. So trying to do this with, what was that, 1,500 metric tons of uranium-235. Good luck coordinating that, and also packing it into a small enough area for long enough that it could cause a crazy runaway fusion reaction. But it's important to know that this sort of thing is not impossible, which is cool and terrifying.
Again, impossible. The Manhattan Project also considered one final protection from atmospheric annihilation. In a small volume of air, radiation can easily escape, but in a much larger volume of bomb-heated air, there is a larger chance that the radiation and energy inside will interact with itself before leaving. Inside a glob of star-temperature air, photons of radiation and hot electrons bump into each other, which robs the electrons of their energy needed to sustain potential fusion reactions. The end result of this inverse Compton scattering is even more energy losses in the safety factor equation, increasing the safety factor by up to 400%, and making a very unlikely scenario even more unlikely.
That's interesting. I didn't even think about the inverse Compton scattering, how the radiation could just interact with itself and push each other apart. That's kind of cool.
To be clear, Manhattan Project physicists were skeptical of atmospheric ignition even before the ink on the calculations was dry. But in these numbers, they found all the justification they needed to split the atom, and therefore history, in two. 15 seconds before 5:30 a.m. on Monday, July 16th, 1945, half of the world's supply of plutonium was compressed by conventional explosives into a critical mass. The resulting energy release vaporized the gadget, disintegrated the tower it was hoisted up, and melted the sand around the site into radioactive glass. A mushroom cloud rose into the morning sky, a second sunrise, as the scientists described it, and instantly became the symbol of the nuclear age. Manhattan Project scientist George Kistiakowsky was reportedly knocked to the ground, even though he was 5 miles away. He got up and ran over to Robert Oppenheimer, who was nearby. "Oppie," he said,
Oppie?
"you owe me $10.
That's awesome.
In most of the reports you'll read, the scientists doing these calculations were satisfied with their conclusions, but fears about igniting the atmosphere have persisted in public consciousness since the 40s. Obviously, the world didn't end with Trinity, but I'm struck by how just a few calculations were enough to dismiss a brand new existential risk and move forward headlong into the atomic age. But it
Well, they were bounding calculations where they made a bunch of very conservative estimates just to be sure that this sort of thing wouldn't happen. Again, in my other video where I talked about the math, I showed an example of how I did bounding calculations for modifications we made to my nuclear power plant after the Fukushima event, just to be absolutely sure all of our additional power sources we provided were more than enough to protect us in the event such a disaster could occur again. So yeah, while these calculations are simple, I just want to emphasize this is a very quick way to prove a point that something is safe or not safe. A bounding calculation is a go, no go. That's very conservative. That makes it pretty easy to make your decision. So while it is simple, it is more than effective.
be said that the gravity of what had happened there in the desert that day was not lost on Oppenheimer or his colleagues. Many of the scientists present were haunted for the rest of their lives.
Few people laughed. Few people cried. Most people were silent. I remembered the line from the Hindu scripture, the Bhagavad Gita. Vishnu
The famous quote.
is trying to persuade the prince that he should do his duty, and to impress him takes on his multi-armed form.
I'm always taken aback by the emotion when he says this.
Now I am become death, the destroyer of worlds.
Yeah.
I suppose we all thought that one way or another.
I always like Kyle's stuff. It's a very well done narrative that shows primary sources within from the actual calculations and experiments. It's all very, very fascinating stuff to watch. Hey, if you prefer peaceful uses of nuclear energy and nuclear technology, please join me on a journey to a clean, safe, sustainable nuclear energy future by liking, commenting, and subscribing. Thank you very much for watching. I'll see you next time.